intro to trigonometry. We're going to focus on our 6 trig functions and then learn about special triangles in this video. The first thing I want to emphasize is that when we talk about SOHCAHTOA and our trig functions, we have to be very careful and make sure that we are only applying these to right angle triangles. So let's first investigate our right angle triangle. Before we can apply our sine, cosine, and tangent, we need to identify the sides of a right angle triangle. And we use 3 different words to identify the sides. We use opposite, adjacent, and hypotenuse. Now, how we identify those sides is all relative to the angle that's given in the right angle triangle. So in this case, the angle is theta and it's in the bottom left corner. So when we identify a side and we use the word opposite, we're saying which side of the triangle is opposite of the angle that we're talking about. So opposite would be the right hand side here, because it is actually opposite of the angle. Hypotenuse is always going to be across from the right angle, no matter what triangle it is. And adjacent, which also means attached to, is going to be that last side. Adjacent is never the hypotenuse. They have to be separated. So although you can see that the hypotenuse is adjacent to the angle theta, it is already identified as the hypotenuse because it's across from our 90 degrees. So therefore, the other leg of the right angle triangle is named the adjacent side. Our trig functions are ratios that are put together that compare the lengths of the sides of a right angle triangle. And the acronym SOHCAHTOA helps you remember 3 of the 6 trig ratios that we're going to talk about today. Now the 3 that we're starting with are sine, cosine, and tangent. So let's start with sine. In the acronym SO, you'll see it starts with an S. That S corresponds with the S for sine. Next to that, you have an O and an H. The O represents the numerator, and the H represents the denominator. So you'll see in the equation here that sine theta is equal to opposite over hypotenuse. For cosine, the C here represents the C in cosine. Then we have our numerator and denominator. So we have adjacent over hypotenuse. Then we have tan, so the T represents the tan. And then we have our numerator and denominator. So opposite over adjacent. So the question is, what do we do with all this information? Well, we use this information when we are trying to identify angles and side lengths of specifically a right angle triangle. Now earlier I referenced that we have 6 trig functions. We have the original sine, cosine, and tangent, but then we also have their reciprocals. Their reciprocals are a little bit harder to remember. They are cosecant, so sine is paired with cosecant. When I say that they're reciprocals, that means that the original ratio for sine, which is opposite over hypotenuse, is now the reciprocal. So the denominator has become the numerator has become the denominator. For cosine, the reciprocal is called secant. So cosine is adjacent over hypotenuse, and the reciprocal is hypotenuse over adjacent. And tangent, which is opposite over adjacent, has the reciprocal named cotangent, which is now adjacent over opposite. You will have to take some time to review and memorize these 6 trig functions. Now let's put them to work. On the right-hand side of example 1, we have a right angle triangle. An angle is identified by theta, and we're given the lengths of all 3 sides, so we actually don't need to solve the sides. The question is asking us to write down the 6 trigonometric ratios. We're going to start by writing the 6 ratios down. I wrote them down so they pair horizontally with their reciprocal, meaning that if we can identify sine, cosine, and tangent, then we've already found cosecant, secant, and cotangent because all we have to do is take the reciprocal. Let's look at the right angle triangle and name the side. So we need to use opposite, adjacent, and hypotenuse. Let's start with hypotenuse. It's always opposite of the right angle. So in this case, it's going to be 29. The angle is our theta. Opposite will be across from it, so that's going to be our length of 21. And then adjacent will be attached to the angle, and it'll be 20. Now let's fill in our 6 trigonometric ratios. Sine is O over H, which is opposite over hypotenuse. Opposite is labeled 21, and hypotenuse is labeled 29. At the same time, I'm going to complete cosecant. I'm going to take the reciprocal of it, so that will be 29 over 21. Cosine is adjacent over hypotenuse. Adjacent is 20, hypotenuse is 29. I'm going to do secant at the same time by taking the reciprocal, 29 over 20. Tangent is opposite over adjacent. Opposite is 21, adjacent is 20. And I'll do cotangent at the same time by taking the reciprocal. These are the 6 trigonometric ratios, and that's all the question is asking us to do. Example 2 is a similar question. It's set up differently based on the information that's given to us in the question. Remember, our trig functions only apply to right angle triangles. So we're going to take the information that was given to us and apply it to a right angle triangle. Here is my right angle triangle, and I get to pick where I put theta. Now it doesn't matter which angle you put it in, as long as you name the sides appropriately based on the tan theta that's given to us. So remember, tan is opposite over adjacent. So if I name the angle in the bottom right corner here, my opposite side will be the height of the triangle, and the adjacent side will be the bottom leg of the triangle. Now the difference between this question and the question before is we have to do one step first to find the length of the hypotenuse. So we're going to use the Pythagorean theorem. 15 squared plus 8 squared is equal to x squared. When we solve for x, we end up getting 17. Now we can find the other trig ratios. We only have 5 left to find because we were given tan. So if tan theta is 15 over 8, then we already know cotangent theta because it's the reciprocal. So 8 over 15. We'll find sine and cosecant and cosine and secant. So sine is opposite over hypotenuse. Opposite is 15 and hypotenuse is 17. So we have 15 over 17. Therefore, cosecant is 17 over 15 by taking the reciprocal. Cosine is adjacent, which is 8 over hypotenuse, which is 17. So secant is 17 over 8. Now we have found the other 5 trigonometric ratios. The last thing I'm going to talk about in this video are 2 triangles called our special right triangles. They are triangles with the measure 45, 45, and 90, and 30, 60, and 90. So there's a special relationship between the lengths of the sides of these triangles. The first thing I want you to remember, if we're looking at the triangle on the left, when we have 2 angles that are 45, that means that their opposite lengths have to be identical. Because these are both 45 degrees, that means that the lengths of the opposite sides have to be the same number. Well, since this is a right angle triangle, if we were to use the Pythagorean theorem and use a squared plus a squared is equal to our hypotenuse squared, we would simplify this to end up getting a square root of 2. With our 30, 60, 90 degree triangle, I'm going to identify the length of the 30 degree angle to be a, so our smallest length, and across from our 60 will be a root 3, and across from our 90 is going to be 2a. So these are our special right angle triangles. I am giving them to you, and we will use them to apply and solve triangles. You do need to know these. We use special triangles a lot. We use them to build our unit circle, and we use our unit circle to graph our trigonometric functions. So they are really the foundation of all trigonometry. Looking at the example on the bottom left, we have 60 degrees identified, meaning that we know the other angle is going to be 30 degrees because all angles inside of a triangle have to add to 180. Now, I'm going to apply our right angle special triangle to this. Across from the 30 will be our A. Across from the 60 will be a root 3. So notice I'm just using the labels or expressions that I have in our special triangle. Across from the 90 is 2a. We're going to start by equating the length to the expression to solve. So 4 is equal to a square root of 3, and then I'll solve for a. The reason I want to solve for a is because a is used in the expression of both other sides of this triangle. So therefore I can find the lengths of those triangles. I will divide by root 3. So I get a is equal to 4 root 3. Now remember, we can never leave a radical in the denominator, so we have to rationalize this. In order to rationalize, we multiply the numerator and the denominator by root 3. So we end up getting a is equal to 4 root 3 over 3. So if a is equal to 4 root 3 over 3, we've already identified that x is equal to a. So we don't even have to do any more work, and we know that x is now equal to 4 root 3 over 3. We also have identified that y is equal to 2a. So if y is equal to 2 times a, if I plug in my value for a, which is 4 root 3 over 3, and simplify, that simplifies to be 8 root 3 over 3. And now we have all angles and all lengths of the sides. And we did that by applying our knowledge of special triangles. In the last question, you'll notice that the angle given is 51 degrees. That is not part of our pattern for one of our special triangles. Therefore, Since it's not a special triangle, we're going to use SOHCAHTOA in order to solve for x and y. 51 is our given angle. So we're going to start by identifying our sides as opposite, hypotenuse, and adjacent. Now we need to determine what we want to solve for. So we're just going to start by solving for x. Well, x is opposite, and the only other side length we can use will be our hypotenuse, and that's because we actually have a value for the hypotenuse. If we used adjacent, we would have two variables in our function. The trig function that applies to opposite and hypotenuse is sine. We have sine theta is equal to opposite over hypotenuse. So let's plug in all the values that we know. Theta is our angle, and the angle in the question is 51. So sine 51 degrees is equal to opposite, which is our variable x, over the hypotenuse, which is 8. I'm going to cross multiply to get x by itself. So we get 8 sine 51 degrees. You go to your calculator, put this into your calculator, and you get 6.217. Now we're going to do the same thing for y. So if we're going to solve for y, we need to use adjacent, and we'll also use the hypotenuse. Adjacent and hypotenuse is cosine theta, adjacent over hypotenuse. Let's plug in what we know. We know that our theta is 51, and our adjacent is y, and our hypotenuse is 8. We cross multiply, so we get 8 cosine 51. Plug that into our calculator, and we get approximately 5.035.